Welcome to this lecture of microscale transport process. In today's lecture, we are going to introduce a new topic, which is basically the immiscible flow in microfluidic channels. By immiscible flow, I mean when there are two phases and the two phases are flowing through the microchannel, and these two phases are not miscible like water or oil or water or gas. So there could be droplets or bubbles. So that is how the two phases can coexist, and if you want to have these two phases flowing through a microchannel, the physics would be somewhat different from what you have for a single phase. In this context, couple of things needs to be defined first. So what we are working with is immiscible flow, and first topic that we briefly touch upon is something called Laplace pressure. This I presume you are already familiar with in other contexts. I just briefly touch upon this. Let us think of a sphere. Let us think of a sphere of radius r. So the surface area is equal to 4 pi r square. Okay. So if this radius changes by dr, increase of r by dr, this changes the interfacial area. Increase of r by dr, this changes the interfacial area. So if I write change in interfacial area, dA, that is equal to d of 4 pi r square, that is equal to 8 pi r dr, and associated increase in interfacial energy, that is du, let us say, and that du would be equal to sigma into dA. Okay. What is sigma? Sigma is the surface tension. So what does this term mean? Du is equal to gamma, du equal to sigma dA. What does this mean? What this means is that what is basically the energy? Energy is equal to the work done, that is equal to force into displacement. All right, force into displacement, and go to the unit of interfacial tension. Do you remember how the interfacial tension was derived at that time? What is the unit of intersurface tension? That is basically Newton per meter, right? That is the unit, that is the unit of surface tension, Newton per meter. Okay. So Newton per meter, you are multiplying it with dA, which is an area term, I mean to say meter square. So essentially what you are getting is Newton meter. Newton meter is the force into displacement. So that is the energy. So associated increase in interfacial energy can be given by du, which is equal to sigma dA. Now if you have, if I say that the force is coefficient of proportionality between increase or decrease of energy of the system and small displacement delta x. So, force is considered, it is the coefficient of proportionality between increase or decrease of energy of the system and the small displacement. That means, force is basically the energy divided by dx, the displacement. If we look at it this way, then what we write here is u is equal to the energy minus integration f dx, basically the increase or decrease of energy that is defined by the sign. So, u is equal to integration of f dx. Okay. So, or in other words you can write f is equal to minus du dx. All right. So, in this case, with this du, this information available to you, du is equal to sigma dA, what do you have for this sphere? We started with a sphere of radius r. Okay. So, we are talking about a bubble of radius r inside say water, and we are trying to find out what would be the force in this case. Let me put it here. The if I write this, so pressure exerted by the interface, we call this say PL, that is equal to force divided by area, and force in this case for the sphere it would be sigma into 8 pi r du dx. That means, this is equal to sigma dA dx, right, and what or dA dr. I mean, if you want to write this in r coordinate, if you want to write this Fr, what would be Fr? Fr would be equal to sigma into 8 pi r, right, from this expression. So, what you have is sigma into 8 pi r, and in that case PL would be equal to F by A, that means equal to sigma into 8 pi r divided by what is the area, 4 pi r square, that means equal to 2 sigma by r. So, what is, I mean, why are we getting into this, and what is the I mean, what are we trying to conclude? The conclusion that I draw here is, for first I write it and then let us see if we can, if it makes sense. For bubble of gas in liquid or droplet of one liquid in another, the pressure inside the bubble or droplet is higher than the pressure in the surrounding liquid by PL. So, what are we up to here? We said that we started with a sphere of radius r, and I said that if somebody wants to change the interfacial area dA, change the interfacial area by dA, this sphere of radius r, a bubble of radius r that had an area, that area is 4 pi r square, where r is the radius of the bubble. So, if there is a change in interfacial area, and if we call this dA, then because of that there would be associated increase in interfacial energy, and because of that there would be a force existing. So, there will be some extra pressure exerted by the interface would be this quantity. So, what we write here is for bubble of gas in liquid or droplet of one liquid in another, the pressure inside the bubble or droplet is higher. Pressure inside the bubble or droplet is higher than the pressure in the surrounding liquid by this quantity which is P L. Okay. Now, that means now P L is equal to what? P L is equal to 2 sigma by R. That means, smaller the bubble, higher the pressure inside the bubble, smaller the bubble, higher the pressure. So, if somebody assumes a bubble of air in water for bubble of air in water, you can assume sigma to be equal to 70 millinewton per meter. All right. Now, if somebody tries to find out this quantity P L for 1 millimeter bubble, 1 millimeter, the size is of the order of 1 millimeter. If somebody tries to find out P L for size of the order of 1 micrometer, and if somebody tries to find out this pressure, this extra pressure that will be there inside the bubble for size of the order of 1 nanometer, one will see that this quantity for 1 millimeter bubble is 1 by 3000 atmosphere. This quantity is for 1 micrometer bubble, it is 3 atmosphere, and this quantity here is 3000 atmosphere. All right. So, this is the difference, and what would be the repercussion? One repercussion, I mean one important significance of these data that I cited just now is that if there is no pocket of gas on the inner wall of a container, nucleating nanoscopic bubbles in the bulk is, I mean it requires effort. Let us put it this way. Probably I should write here is that it requires superheating, effort in a sense. I write this as superheating. What I try to write here is, if there is no pocket of gas on the inner wall of a container, if suppose you want to boil water in a pot, and if there is no such support from no such artificial nucleation done, I mean no such arrangements, no such platforms present for nucleation, then if it has to nucleate on its own inside the bulk, that means you have to, the bubble has to form inside the bulk of the liquid, and that has to be a nanoscopic bubble. It requires, so you have to break this barrier, you have to provide that kind of pressure, then only the bubble would be generated. So, that is what I would like you to appreciate here, is that this pressure can be quite significant when the dimension of the bubble is small. Now, we have been talking about only one radius. We said that this PL is equal to 2 sigma by r. I mean, we are just working with a sphere, just a single sphere, but you may not have a sphere all the way. You can have a curvature which will run like this, or you may have an interface which will be something like this. This may be the interface. Okay. So, you have to make note that you can have something called a curvature. And what would be that curvature? You can form, suppose this is the interface, then in that case you can draw something called a tangent circle. Tangent circle that goes through the point of interest. On the interface. Okay. Now, the radius of this tangent circle, is referred as radius of curvature. Radius of curvature. This is a vector. First of all, this is a vector. So, the curvature, as such, the curvature is a vector, and this is pointing to the center of the circle. So, curvature is a vector, pointing to the center of the circle. What that means is, if you want to draw another say this portion, here the curvature is different. I can see the curvature is little turned like this. So, it may be that the circle goes in the other direction, it may not come inside, and so this would be the tangent circle, and then that would be the radius of curvature. All right. Now, there is another issue here, is that when it comes to 2D surface in a 3D space, when we are talking about curvature, of 2D surface in 3D space, this can be expressed in many different ways. 2D, I mean curvature of 2D surface in 3D space. Basically, what you write here is something called a mean curvature, which is given by this term, let us call it this k, which is equal to half of k1 plus k2, where these two quantities k1 and k2 are principal curvatures. Now, the question would be, what is principal curvature? Think of curvatures of curves resulting from intersection of the surface of interest with all possible planes tangent to the vector that is normal to the surface at the point of interest. The largest and the smallest curvatures are principal curvature. So, what I mean here is that when it comes to a 2D surface in a 3D plane, okay, so in a 3D space you have a 2D surface. So, you can have curvatures of curves resulting from intersection of the surface with all possible planes tangent to the vector. So, suppose this is the point of interest, say let us think of this to be the point of interest. Okay. So, you have something perpendicular to this point of interest. Okay. Now, when it comes to a 2D surface, this I have drawn here is 1D, just a single line. When it comes to a 2D surface, okay, in that case there could be several such planes tangent to the vector that is normal to the surface at the point of interest. That means, there could be you have drawn a circle, you could have drawn a circle like this, you could have drawn a circle like this. So, there could be several such circles possible, and you can have several such curvatures also possible. So, the largest and the smallest are referred as principal curvature, and you take the mean of that and call this mean curvature. Now, so you need to understand there are two terms we have already we are toying with. One is the curvature, another is the radius of curvature, and one is the reciprocal of the other, that you need to understand. So, what we do here is, if we want to write what is PL in this case, we would be writing PL as sigma divided by 1 by R1 plus 1 by R2. There was 2 sigma by R, right? We had what was there for the sphere? For the sphere we had it as 2 sigma divided by R. Instead of R we have 2 into, instead of R we had that time as 2 sigma divided by R. Instead of that we have now that R is replaced by, or rather R by 2 is replaced by 1 by R1 plus 1 by R2. Okay. So, basically your K1 here is 1 by R1, sigma into 1 by R1, is that so? I am sorry, yes, yes, it is sigma by R, exactly, it is sigma by R. So, it should be PL is equal to sigma into 1 by R1 plus 1 by R2. So, that is it. So, earlier you had 2 sigma divided by R, now it should be sigma into 1 by. So, these represents so 1 by R1 represents the curvature here, all right. Now, the fact is that the points at which the curvature is the highest are the points most stretched, points most stretched are the points of membrane most stretched. So, the pressure would be highest there. So, if you if a droplet or bubble is squeezed away from spherical shape, if it is squeezed away from spherical shape, then the result would be you will have higher regions of higher curvature and regions of lower curvature. That was not the case with that was not the case with the sphere. When it was originally in its when it is originally in its spherical shape, when the droplet or the bubble is originally in its spherical shape, it is sphere and the curvature is same everywhere. Now, if somebody squeezes that droplet or bubble to a non-spherical shape, that means in some places there will be higher curvature and in some places there will be lower curvature. So, automatically points at which the curvature is highest are the points of the membrane most stretched. So, pressure is the highest there. So, automatically regions of higher curvature and lower curvature, there you will have an imbalance. There will have an imbalance in Laplace pressure. There would be an imbalance, means at higher curvature you have a different pressure than the lower curvature, and this imbalance will drive the liquid. This imbalance in Laplace pressure, this imbalance will drive liquid to a perfectly symmetric sphere. So, this is one point you need to remember, that it is the spherical form, it is the perfectly symmetric spherical form that a droplet or a bubble will acquire. If you squeeze and then let it live on its own, it will acquire that spherical shape. The other point here is what we call spontaneous breakup into bubbles and droplets. Spontaneous breakup into bubbles and droplets. Think of a cylinder of gas or liquid. Think of a cylinder of gas or liquid surrounded by an immiscible fluid. So, we are talking about a cylinder. A cylinder surrounded by another fluid. So, it can be a cylinder of air surrounded by water, or it could be cylinder of oil surrounded by water. Now, if somebody tries to find out what would be the radius of curvature, if he picks up some element, and if he picks up the radius of curvature of that element, then what he will find is there is a curvature in this direction I can understand. However, there is no curvature in this direction, so you can consider that to be that radius to be infinity or curvature to be 0. That can be considered, but you have one curvature is already there, where the radius is simply the radius of the cylinder. So, if you look at the curvature of the cylinder, that is how you would treat this. So, you have, when we talk about the principal radii of curvatures, principal radii of curvature, radii itself is plural, then you have one which is axial curvature and the other one is radial curvature. This axial curvature for the cylinder, this is equal to 0, and for radial curvature, this is equal to the radius of the cylinder. Now, there is one point here, is that these liquid columns are never perfect, and there will be small deformations. There would be small deformations of shape due to various reasons, if not anything due to thermal fluctuations. So, if there is small deformations of shape, then it will appear something like this. Instead of the cylinder, that wall of the cylinder will appear something like this. So, in that case, if somebody looks into the peak, if this is called a peak and if this is called a trough, so they will find that in this modulation, the radial curvature at the peak is smaller than the same at the trough. Why is it possible? Because here the radial curvature means we are talking about this distance, and here the radial curvature means we are talking about this distance. I mean curvature, radius of curvature, by radius of curvature at this point we are talking about this distance, and here radius of curvature we are talking about this distance. So, when it comes to 1 by this quantity, you will find that curvature is basically 1 divided by, so it is just the reciprocal of it. So, radial curvature at the peak would be less than the same at the trough. Okay. So, and if somebody tries to find out, there would be an axial curvature being generated because of this modulation. Earlier, when you had a cylinder, there was no axial curvature, it was all straight. So, that is why you considered that axial curvature to be 0, the radius of curvature for the axial curvature is infinity. But now, since there is an undulation, so there would be an axial curvature present. So, if you try to find out, you will find that the axial curvature, for that what you need to do is you need to draw a circle and find the tangent. Here you need to draw a circle which is in the circle would be in other direction, the center of the circle would be outside the cylinder. Okay. So, what you will find is that the axial curvature at the trough is oriented outward Okay. So, when it comes to the Laplace pressure, if you compare Laplace pressure at the peak and if you compare Laplace pressure at the trough, you will find that this particular aspect, this will cause Laplace pressure at the peak to be less than Laplace pressure of the trough, whereas this particular aspect will bring Laplace pressure at peak to be greater than pressure at the trough. So, the influence of this particular aspect is like this and influence of the second aspect is like this. Now, these first one, these will happen when for a modulation or for okay, we call it modulation at larger wavelength, whereas this particular aspect will happen for modulation at smaller wavelength, a shorter or should I call it, instead of smaller, it should be shorter wavelength. In this case, basically this I mean why I am writing this is probably this Laplace pressure will become negative, since the circle goes in for the trough, the circle goes outside the cylinder. So, probably this will become negative. Now, if you now the fact here is that when this happens, Laplace pressure of peak is less than Laplace pressure of trough. What that means is fluid will be driven, this condition implies fluid will be driven from trough to peak, because trough is at a higher pressure. So, fluid will be driven from trough to peak. So, if the fluid is driven from trough to peak, so that means you are encouraging the perturbation, or you are amplifying the perturbation. So, this implies amplification of perturbation. Okay. On the other hand, the second case means that the fluid will be driven from peak to trough. This implies decay. So, depending on the wavelength of this modulation, either the perturbation may amplify or the perturbation may decay. Now, for perturbations of shorter wavelength, axial curvature is greater than radial curvature. for perturbations of shorter wavelength. What does shorter wavelength means? If this was the cylinder, for shorter wavelength means, and what is the larger wavelength means? Like this, right. So, for perturbations of shorter wavelength, the axial curvature is greater than the radial curvature. What does this mean? Radial axial curvature is greater than the radial curvature. You for shorter wavelength, you have what is the axial curvature in this case? For example, this one, the axial curvature is here, but for here this one, the axial curvature would be, the radius of curvature would be this much. Here the radius of curvature would be shorter, right. So, this is what we are referring to, the axial curvature, and the radial curvature is this quantity, this curvature we are referring to. So, this is the radius of that cylinder at the peak and at the trough, whatever the variation is, that we are calling radial curvature, and these we are calling axial curvature, here this much, here this much. So, here in this case of short, this is the shorter wavelength and this is the longer wavelength. So, we are trying to conclude that for perturbations of shorter wavelength, the axial curvature is basically the inverse or the reciprocal of the radius of curvature. So, axial radius of curvature is basically less than the radial radius of curvature. In this case, that means what I am saying is, this is the case of a shorter wavelength, and in this case the axial radius of curvature, which is this quantity, this much, is much less than the radial radius of curvature, which is this quantity, whereas in this case it is the other way. So, for perturbations of shorter wavelength, the axial curvature is greater than the radial curvature, and so you are saying that the Laplace pressure finally, I mean, this is the conclusion we are making, that the Laplace pressure arising from these deformations leads to decay, all right, and the converse is converse would be for longer wavelength. For longer wavelength, we go through the same argument. I mean, I hope you understood what I said. For longer wavelength, the deformation leads to amplification. So, in this case, there should be a critical wavelength. There should be an existence of critical wavelength. Critical wavelength below which the fluctuations decay. So, I mean, you are saying what you are trying to say here is that for shorter wavelength, if there is a perturbation, that will decay. So, that means it will restore its cylindrical configuration, and if the wavelength is large, how large? So, there has to be some critical, there has to be some limit. If the wavelength is beyond that limit, then it will not decay anymore, rather the perturbation will amplify, all right. So, what is that critical wavelength below which the fluctuations decay and above which the fluctuations amplify? Here, this has been shown, this has been derived by something called a Rayleigh-Plateau. This is referred as Rayleigh-Plateau instability, and it has been derived that this critical wavelength below which the fluctuations decay is equal to circumference of the jet for a stream of inviscid liquid falling through air. So, inviscid liquid, if there is a stream of inviscid liquid and that is falling through air, then critical wavelength below which the fluctuations decay is equal to the circumference of the jet for a stream of inviscid liquid is equal to the circumference of the jet. Okay. What you can and another I mean this has been derived. I mean somebody as I said, in Rayleigh-Plateau instability, there it has been derived using a sinusoidal modulation, and then this has been shown that this is the critical wavelength. Another aspect here that I must mention is that the wavelength this also has been derived, the wavelength that provides fastest growth of perturbation is almost equal to 1.43 times the circumference. The wavelength that provides fastest growth of perturbation is close to 1.43 times the circumference of that cylinder. So, what these two criteria, more importantly the second criteria, what this defines is characteristic diameter of droplets. What this means is, think of there is a problem of dripping faucet, which you are many of you are already aware of, that when a water is dripping from the tap, if there is a thin thread that comes out from the tap, beyond a distance it breaks down and it forms a spherical shape. It takes a spherical shape. The cylinder breaks. Okay. Beyond what distance it breaks, and what would be the characteristic diameter of that water droplet that forms, that can be I mean the theory behind that instability, theory behind that breaking of that droplet, that is covered by this Rayleigh-Plateau instability criteria, or rather Rayleigh-Plateau instability theory. So, these are not just empirical facts, these are already derived, this derivation is already available. Okay. Now, when the breakup takes place inside a channel, when the breakup of droplet takes place inside a channel, the breakup process can be different. Or when it happens, what you can write is that the viscous effect of transport of continuous fluid to collapsing trough can slow down the breakup. Do you understand what I am trying to say here? That in a dripping faucet you have an infinite medium and through which the water is simply dripping. Now, if it does not happen that way, instead if you have a channel in which there is some continuous liquid is there and within that you are trying to create droplets. In that case, if you are relying on this Rayleigh-Plateau instability to guide formation of droplets, you must appreciate the fact that these breakup of droplet is taking place because there is fluid being transported from the peak to the trough, or from the to stabilize, or from trough to the peak to amplify. So, that transport here you have considered, and what did we say, the word that we used here is inviscid liquid. We called that inviscid liquid. So, it is a potential flow problem, but when it is inside the channel there will be viscous effect for that movement of liquid from trough to the peak, and that is basically instrumental in breakup of droplets. So, these also needs to be considered. So, it would be it is somewhat different. I mean, the breakup process, it will slow down. I mean, you cannot make your decision based on that these criteria that I mentioned, that wavelength should be 1.43 times the circumference. This cannot be generally applied to other situations. That is all I have to say as far as today's lecture is concerned. In the next class, what I will do is, first I will define a few dimensionless numbers which are important for immiscible flow through microchannel. Those are, for example, capillary number, Bond number, Weber number. So, I will first briefly introduce those dimensionless numbers, and then I will go straight away to the motion of a droplet or a bubble through a microchannel, because that will there you will find that the pressure drop, if you had them flowing separately, if you are flowing just simply the gas or simply the liquid, and you calculate the pressure drop, and if you assume that since I am introducing bubbles which are basically the mixture of two, so the pressure drop would be halfway, it will not be the case. Rather, there are lot of complex dynamics coming into play, and we will get into the movement of the bubbles and how the pressure drop is how you derive the pressure drop in such situation. So, we will first introduce the dimensionless numbers, and then we will get into finding how a bubble will move. That means, you are expecting the bubble to be there and surrounded by an annular liquid, okay, or a droplet to be there surrounded by the other liquid, which is the continuous phase, and now you are having a motion. So, what would be the thickness of that annular film, let us say, or what would be the pressure drop under such situation. So, that we will get into in the next class. Thank you. That is all I have for today.